Hello YouTubers and fellow hams. I'm down here at the bench on this cold February morning. And it's cold. Did I say it's cold? It's cold. Anyway, a while back, in a birthday edition What's in the Box episode, we received this HP 8640B signal generator from Rick out in California. Thanks, Rick. Thanks again. And I promised you guys that we'd take a good look at it. So I thought, hey, we'll get started on that video today. We'll take a look at the 8640B, see what it does, how it works, what's inside. Thing's built like a tank. It's 52 pounds. Sitting here on my bench, I made a little room for it. But you know, before I can really dig into it, it has a defect that I think we need to address. And that defect is right there. Right there. Power switch, or lack thereof. There should be a push button right here. Instead, there's an opening. The plastic part of the push button's gone. Let me give you a close-up. All right, so here you can see the hole where the power button used to be. Now I've got the power cord unplugged so I can demonstrate that this actually still works. If I push in, clicks, it stays in. Push in again, clicks and releases. And inside of there's a little metal barrel. That's what's actually going in and out. I don't know if you can see this on camera or not. So the switch has this little metal barrel, and there's a little pin in the middle that I guess would have held the button in place. And that whole barrel moves in and out, in and out. So we really just need a cylindrical shape that'll fit in this barrel that comes out and has a larger cylindrical shape that would be the push button. So that should be pretty easy to do on the 3D printer. So I'm going to get some paper out and my ruler and my calipers. I'm going to make some measurements and go up to Tinkercad and design a push button and 3D print it, and then we'll come back down and see if that works. And if that fits, we'll go ahead and fire this thing up and show you how the machine works. Well, it took a couple of revisions to get it exactly right, but there is the replacement power button. Initially, I didn't make it quite long enough. That's a deep power socket, but it fits in there just fine, and there we go. Works perfectly. How about that? Replacement power button. Yay for 3D printers. Woohoo! Well, now that we've got our nice new power button on the unit right there, I might reprint that in black. I don't know, the gray's okay, but I might reprint that in black just so it goes with this black bezel up here. Nice thing with a 3D printer, you can make those choices. But anyway, we'll take a closer look at the unit itself, what it is, what it does, and how it works. Now it's warming up. It's been on for about 15 minutes, but probably should be on for at least a half an hour, especially since the basement is currently at 55 degrees. It's got a little ways to go to warm up. But its accuracy is pretty good. I've already checked it against the frequency standard in my Marconi and zero beat it against WWV, and it's pretty spot on. Right now it's spitting out 10 megahertz. It's flickering on that last digit there to a 1, but if we look over at the frequency counter over here, 10.00005, and that's drifting down as it warms up. The drift is slowing down. Yeah, I know it's a Heathkit frequency counter, but you know, I've tested that, and I've tested it against a HP that Rick sent me when he sent me the Marconi. Got this HP 5382A, right, which is dead on. And the frequency standard in the Marconi seemed to be dead on. And the Heathkit agreed with it, you know. So the Heathkit, I did tweak it just slightly using that frequency standard, so it agreed with everything else. But what I found was that this Heathkit is more sensitive than the HP. I ran the same signal into both, and as I brought the signal level up, the Heathkit latched onto it about 20 to 30 microvolts earlier than the HP did, so it's more sensitive. So I'm keeping the Heathkit on the bench for now. But anyway, the HP, what does it do? Well, it is a frequency source. It generates a sine wave output at a frequency from anywhere from 500 kilohertz to 500 megahertz, very precisely controlled. You've got a large vernier here to grossly adjust the frequency. You can see the frequency counter's not fast enough. There we go. I can move it quite a ways quickly with this. Get it close, and then you've got a fine-tune control here to let you dial that in to get it where you want it to be. And once it's warmed up, it's very stable. Over here, we have control over the output voltage of the generated signal, very precise control. Little switch up here will turn off the RF output and turn it back on. Next over is the range, and there are several ranges from 0.5 to 1 megahertz, and you can just rattle up through there, and it goes in steps: 2 to 4, 4 to 8, 8 to 16, 16 to 32, 32 to 64, 64 to 128, of course, which would leave the last one 128 to 256. A very binary relationship there, isn't it? It's like we're switching in another digit in the binary sequence each time. And then finally 256 to 512. And if it had an external reference, you could go up to 1 gigahertz. But this one does not. It tops out at 512. So you set your range here. So I've got it set to 8 to 16 megahertz, and I've dialed this into 10 megahertz roughly. Tweak that up to where we're at 10. So real good precise control over the frequency and voltage of your source. Then over here we get to modulation. This will provide both FM and AM modulation. And you have, in FM, you've got the deviation, 5 kilohertz, 10 kilohertz, 20, 40, 80 kilohertz, 160, 320, all the way up to 640 kilohertz of deviation. And then it goes up to megahertz. So you could actually get this thing to deviate by 5 megahertz in FM modulation. I can't imagine a case where you'd need to use that. For working on ham gear, 5 kilohertz deviation is going to be fine, because that's our narrowband FM on our UHF and VHF handhelds. Then you've got modulation type: off, internal, which would be an internal oscillator source. And then there's a connector here where you can input a source for your modulation. So you could almost use this as a way overkill transmitter by feeding audio in here, and then setting this to AC or DC coupled for this input. So it'll take your external audio as a modulation source. And then we have pretty much the same thing here for AM. Over here we can adjust our modulation percentage or output, modulation output. From 10 millivolts up to, or actually from 1 millivolt up to 3 volts modulation source. So in here, the same switch settings as over here. We have an internal source and then AC or DC coupled from an external input for AM modulation. And then here in the middle is the frequency of the internal modulation source. Right now it's on 1 kilohertz, 1000 hertz. That would be the tone that we would hear. To demo that, over here, I have the little Yaesu FT817, And I'm going to take the RF output from the the signal generator, and plug it into the antenna. And I'm on 10 megahertz AM, and I can hear something. Okay, no microphonics, that's good. I'm going to turn on modulation over on the signal generator. And we'll turn on AM internal modulation. And I don't know if you can hear that. There is our modulated signal. I'll put the Yaesu on FM mode, and we'll turn on FM modulation. And again, same tone. There it goes. Yeah, that switch definitely needs attention. So, modulation controls over here. Up here is the meter, which gives you a more analog and more precise reading of things like your voltage output, signal output. Right now it is set for measuring level in volts. You can also read percentage of AM modulation and FM modulation deviation by pressing these buttons. And let's see, let's go to AM. We'll set our modulation to internal. Okay, 0 to 10 light is on, so we're using the 0 to 10 scale. So does that mean that we are at 8 times 10% is what it says on the button? So does that mean we're at 80% modulation? I don't know. I do have the Marconi running up here, so let's put my output into the input of the Marconi. And let's see here. AM modulation, 78%, 78.1%. And this meter down here on the HP is reading just below 8. So if I move that up to where that's on 8, which I thought would mean it's 80%, by golly, the Marconi says that we're at 80% modulation. So yeah, I guess that's how that works. Isn't that cool? So the HP 8640 is just a wonderful signal generator. I mean, it's old, it's heavy, this thing is huge. It's about 50 pounds, but it's made to be lab gear. I'm just thrilled to have it. It's heads and shoulders and light years beyond what I used to have, which was an old Heathkit RF oscillator, which was not precise at all. So this is leaps and bounds above that as far as precision goes, and I should be able to do full alignments on radios now, which I've been limited on how much I could do with that old Heathkit signal generator. So I guess the only thing left to do is I'm going to show you what's inside this thing. I'll pull it out here on the middle of the bench, reposition the camera, and we'll take the top and bottom covers off and have a look at how well built it is. On the back of the unit, not a lot to see. We obviously have our AC input over here, fuse, a BNC jack for an external time base. If you were using this in a lab with a bunch of other gear, you probably would have an external rubidium-based or some other high-precision time base that would feed all your gear, so they would all have the same reference and be in sync with each other. And there's a switch here for external or internal time base. Now, the side of this very heavy machine, we have a handle, and I believe there's one on the other side too. Yep, handle on each side. So it would take 2 people to carry this bugger. Okay, I need to raise the camera up so we can look down inside, and we're going to take the top cover off and take a look there, and then we're going to take a look at the bottom. Top cover has 1, 2, 3, 4 screws, and then it slides back and lifts off. And wow. This looks like some NASA engineering in here. Oh, everything is really, really nicely done. Everything is very labeled. I mean, labeled. Wow. They even have removal instructions printed in here. Swing this around. To remove center section, remove all asterisk marked screws and this screw whoosh, in 4 places. Unplug riser board while carefully lifting upward. So they have very verbose instructions all through here on how to remove everything. Even up in the front here, this little PC board says to remove optional 001 audio oscillator, yada, 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 step by step. Everything is modular. This is one module, this is one module. Counter assembly, so this is the frequency counter. Divider filter assembly, so this would be frequency dividers and input-output filtering. We have a couple of little extra boards back here, but they're labeled right here. 20, plus 20, minus 20 regulator board is what this is. Plus 44 and plus 5 volt regulator board. Negative 5.2 regulator and fan driver board. So that's really nice. I like the way that's all labeled. Here there's a label that says rectifier board and points over to this. And these would be the power supply components over here. Big filter capacitors with these nice plastic covers to isolate them from physically. Wow, from these boards. Here's our cooling fan back here. So yeah, it's all very nicely laid out. These are some interesting little additional add-on boards back here that are just in a riser. So you can just release them and lift them out. And automatic, what is this? It's labeled on the board. Doubler, level. Oh, those are adjustments. Level and meter. Doubler offset driver. And it should just, just like before, it just slides back and lifts off. And there we go. Wow. Now that's interesting. This is the main oscillator assembly. Holy cow. Oh, that's fascinating. I'm going to have to reposition the camera and show you this this arrangement on this front control. It has multiple cams and platters that catch on pins and change which shafts you're turning. That's fascinating. And let's see, this is the switch for output level, which is in a big enclosure again too, with some gold-plated finger contacts at the back. What control is this? This is, oh, that's the range switch. So that's a multi-position switch right there in that big metal box. Woo! Oh man, and to heck with coaxes, they have these hardline interconnects to take signals from one point to another. This is a hollow metal tube, probably with a center conductor. So they're little bitty mini hardline connections, taking the signals from point to point in here. This is just way over. Well, I would say overbuilt, but it's lab gear. You know, it's got to be like that. Okay, that's going to be just a protective cover for that transistor. Again, everything's modular. AM, AGC, RF amp assembly is in this guy back here. And these boards, although not labeled, they're all on these nice little card edges. They can be removed easily. No, they are labeled on the boards themselves. This is a FM, AM audio oscillator. Varactor anode, Varactor cathode, FM overload. Oh, interesting. And the transistors that are on these things are all the old CAN types. Oh, that's an IC there. Looking for a brand name on one of those transistors. Hong Kong. That's all it says on it. Hong Kong with a number. But yeah, gold. They're gold-plated traces on this PC board. And a lot of people think that they use gold for conductivity, but actually silver has a lower resistance than gold. The reason they use gold is it doesn't tarnish. That's the main reason for gold in high-precision, well-built electronics. It doesn't tarnish. It's actually about the same resistance as lead, which it's molecularly very close to. I think there's only, what, 1 electron difference between lead and gold. So anyway, I'm going to move this around, and I'm going to show you this mechanism over here. Down in here, because this is just really cool. Hang on. All right, so what we're looking at here is the main oscillator assembly, and this is the tuning control on the front that sets the frequency. And if you look down here, you'll see that there's multiple platters, and they have these little stops on them. And as they swing around, this stop here just engaged that bottom one, which engaged the ones above it. And they're all coming around together. But if we go far enough, there, see now it's only moving that one. There was a pin down there that stopped the other ones. And now we're just bringing up just one of them. And now bringing up the next two. And then that's separated and moved. See, so that whole cam mechanism there allows these separate shafts to be moved revolution to revolution. See that? So I would love to see what's going on inside of here, but I'm not going to open it up. I am not going to touch this. Well, I just touched it, but I'm not going to open it up because this is probably the most precise piece of equipment in here, since it's the oscillator that's producing the signals. But that is just fascinating right there. The way that those different platters move, and they must be turning different shafts inside of here, or different variable caps. That's just neat. I've never seen a mechanism like that before. Okay, I just had to show you guys that. So, you know, that's the guts of this beast. It's quite a machine, and I am going to have to get the manual out and spend a little more time on it and really learn all of its tricks and how to use it. So, hey, I rambled a bit. Sorry about that. I just really wanted to show you guys this piece of equipment and just talk a little bit about what it can do. I've still got a lot to learn about what it can do. But that is the HP 8640B signal generator. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.